In this three-part series of videos, we're going to expand upon our knowledge of double displacement reactions and take a look at a way to determine whether an ionic compound such as NaCl, that will be the focus of this video, are actually able to dissolve when we put them into a solution, or whether the compound will resist dissolving and stay as a solid in the solution. The purpose of this three-part series is to develop a system that will allow us to better predict which of those two outcomes will happen. Now, in order to explain that, we need to actually talk about what dissolving is and why certain ionic compounds are actually able to dissolve when we put them into water. And to do that, we can simply go to our knowledge of structural chemistry, specifically our knowledge of intermolecular attractions. So, sodium chloride as an ionic compound means that there is a cation, the sodium ion, which is held together in an ionic bond, which allows the cation to attract to the negative charge of the anion chloride here. Now, the reason why water is so critical in its ability to dissolve this is that water is a polar molecule. We know from analyzing its Lewis structure that because oxygen's electronegativity is higher than that of hydrogen, it is going to pull the electrons in these bonds closer to it, giving it a stronger negative charge while giving the hydrogens a partial positive charge as a result. And because of the fact that oxygen also has two lone pairs while hydrogen has none, this amplifies the strength of oxygen's negative pole and allows the oxygen on water to attract to the positive charge in sodium chloride, and conversely allows the hydrogen side, which has positive poles in water, to attract to the negative charge that we find in an ionic compound such as the chloride ion. Now, from the intermolecular forces introduction, we can recognize these as ion dipole forces because this is an attraction between a polar molecule with a dipole, that being water, and a true ionic compound that has full positive and full negative charge. Now, here I have drawn an example where we just have one water molecule attracting to each ion like this. Now, the way that dissolving happens is that water can actually use these ion dipole attractions to pull these two ions apart, because remember that when water is a liquid, all of the water molecules that are in this liquid are not just sitting in the same spot. They're all moving around in basically completely unpredictable directions. But when these water molecules move, because of the fact that the water molecules are attracted to the oppositely charged ion, the movement of water can actually pull these two ions apart. Now, this is a little bit silly to look at, but is it realistic to assume that one water molecule is enough to pull each of these ions apart? And if you said no, it's kind of common sense if you think about it, because the ionic bond that holds sodium and chloride together is a bond between an ion that has a full positive charge with that of an ion that has a full negative charge, whereas water only has a dipole, meaning that it has a partial charge. So one water molecule probably not enough to get these two ions to separate, and there's a simple experiment that you can do from home to test this out. If you take a pile of sodium chloride that's about this size, is it realistic to assume that this much water, only a few millimeters, is able to dissolve this amount of salt? Well, obviously this is ridiculous. You need more water if you want to dissolve more salt. That is essentially what is happening here. This is just at the atomic level. So what if we take a look at what happens when we actually have many individual water molecules that all use their combined ion dipole attractions to attract to each of the oppositely charged ions, and if they all work collaboratively to pull the two ions apart, if we have enough water molecules, you can actually get the two ions separating like this, and at which point where the sodium and chloride ions are physically separated from each other, we can say that this compound has been successfully dissolved. Therefore, if we want to put states of matter next to each of these, when the two ions are present, this would be what NaCl looks like in its solid form, the salt crystals, if you will. But when the two ions have become separated by water, this is what NaCl would look like when it is in its aqueous form. So what is it that actually stops these two ions from being able to get back together? Because all positive charge will want to attract back to negative charge. Well, if we look here, we can see that all of the water molecules that are surrounding each of the ions are forming a physical barrier, or a shell, if you will, that physically stops the two ions from getting back to one another. And as long as they are separate, it will appear as though NaCl has been completely dissolved in water and is no longer visible. And these shells, or physical barriers formed by water, are logically what we would call hydration shells, meaning literal shells that are made out of water, hence the hydra prefix that we see here. Now, the next logical question to ask, since we're on the subject of ionic compounds, is, are all ionic compounds able to dissolve in water? And if you think of a quick example such as calcium carbonate here, we will see that answer is no. So in terms of why, there's a very easy comparison that we can make, and we can take a look at what happens to NaCl when it dissolves and compare that to calcium carbonate here. So when water is able to separate the positive and negative ions from each other, we would have the positive ion surrounded by water so that it's dissolved, and the negative ion surrounded by water so that it is also dissolved, like this. And this process of water separating the positive and negative ions from each other is what we call dissociation. So dissociation is a term that's often used interchangeably with the word dissolving, and they are similar, but it specifically refers to the separation of ions in an ionic compound by water using its intermolecular dipole ion or ion dipole attractions. Now, if we look at what water has to do to separate Na plus and Cl minus, the charge that holds Na plus and Cl minus together is +1 and -1. But if we look at calcium carbonate here, we see that calcium has a +2 charge and carbonate has a -2 charge, meaning that the ionic attraction that holds this together is going to be much stronger, twice as strong, in fact, as the ionic bond that holds sodium chloride together. Now, if this bond is stronger, is it likely that we would need more water or less water in order to force these two ions apart? Well, in order to overcome such a strong positive-negative attraction, we would probably need more water, and it is possible for us to see calcium carbonate dissolve, and you can actually observe this over time because calcium carbonate is the chemical formula for limestone, which is a very common sedimentary rock. So limestone does actually break down over time if it's left to sit in water, but this process takes hundreds, if not thousands of years, as well as a lot of water in order to do this, and we can explain why relatively simply just by looking at the stronger attractive force that exists within the ionic Lewis structure. Now, the third term that we're going to look at in the next series of videos is what happens rather than, instead of having a solid that just doesn't dissolve or dissolves very poorly in water, what happens when we take two chemicals that independently both dissolve in water, such as sodium chloride. We know that you can make salt water by dissolving salt in water, and this is another soluble chemical called silver nitrate. Both of these are colorless and completely transparent, but when the two are mixed together and when the two undergo a double displacement reaction, one of the chemicals, silver chloride, actually forms this white powder that doesn't dissolve in the solution, and this is what we call a precipitate. This is indeed the same word that refers to the formation of water in the atmosphere, which is where we get clouds, except there it's water vapor, a gas turning into a liquid. But here, a precipitate is what happens when we get two solutions that begin as aqueous, dissolved in water, and where one of the products that is produced is solid and therefore is not able to dissolve completely within the solution. Usually the precipitate that forms will be one of its kind, and then the other compound that is made, in this case sodium nitrate, is going to dissolve as well. But again, we'll look at strategies for predicting how one substance is able to dissolve and another substance is not. The final piece of terminology is more of a technical criticism, but if we take a look at the statement, is it possible for an ionic compound to 100% resist being dissolved in water? And realistically speaking, the answer to this is no. Even a dissolving resistant substance such as limestone, calcium carbonate, will eventually dissolve or dissociate if it's left in water for a long enough time. So saying that something 100% never under any circumstances dissolves in water is not really accurate. So instead of saying insoluble, meaning does not dissolve, that's what insoluble does not dissolve, rather, that's what insoluble means. Compounds that form precipitates that are more likely to be solid rather than dissolve in water are said to have low solubility, or alternatively poor solubility instead, saying clearly that it's not as if they don't dissolve at all, but that they dissolve very poorly, or that water is very poorly able to cause them to dissociate like this. In the next video, we're going to go over a set of rules that you can use in order to predict whether a precipitate forms or whether an ionic substance produced by a double displacement reaction is actually able to dissolve in water.